I mean, no curvature, nothing. I draw a line there, and I claim that deformation theory is GRT. And moreover, I moreover claim that this claim is equivalent to Furush's theorem, that hexagons are not important. From this picture, you get this result. From your result, you get this picture. So that's what I'm going to explain. But for me, this was fascinating. It's essentially, just a fine interpretation of one of the results in the paper by Thomas Wilwacher. This is his famous paper of 2010, which I think one of the greatest papers in recent years. So one of the things he did there, which is not precisely his most famous theorem, in fact leads to this geometric picture and its algebraic incarnation. But let me start with comments on my comments, which I made during the talks, and I simply want to make them more precise. I will start with my comment to Drew Barnatan talks. He is the father of a periodic approach to GRT. And I have a feeling you're not happy about it. So let me explain why you should be. So why you should be. So you remember his... You remember... but my point is, you should be proud. I'm going to convince you. So remember his slide. I mean, I think every item on his slide is an operand. Let me just start with the family of pure braid groups, just pure braid groups. It's a non-sigma operand. Let me explain it because it will be then clear how we make operand in other more complicated things. This is a non-sigma operand in the category of groups. So what is the composition? I mean, okay, let me take, say, PB3, Cartesian product PB2. Let me take the composition into the third input. What is it? So let me give an example. So what is a braid? 1, 2, 3. I have fixed ordered points. And OK, what is a braid? I mean, this is something. Let me make this straight. This goes something like this and returns back. It's a pure braid. Let me compose it with 3, say, with this braid. 1, 2. What is the result? Okay, it's clear what we do. I mean, our input is a braid. So essentially what I do, I erase this braid. Just only a smile is left. I make this one very thin. Instead of 3 and 4, I substitute 2 new points, 3 and 4, as usual in operands. And then I just draw this braid along this shadow. This is it. Axioms are obvious. It's an operand. All the axioms are satisfied. So, okay, you understand what I mean. These are just these two. So that's another important operand. Now, operand, he introduced a family of Lie algebras, Corner-Drinfeld algebras, Lie algebras. Remember, these are quotients of free Lie algebras in symmetric generators, no diagonal, modular standard relations. Again, look at his note he gave us with the definition of this quotient. It's again an operand in the category of Lie algebras. Monoidal structure is direct sum. It's important to notice, so that direct sum. Therefore, even zero element acts non-trivially in the periodic sense. So beware. I will use this fact. Even zero element, when we composed with some non-zero element, is something non-trivial. Right? Next, he introduced first an operand, PAB. It's a family of categories of groupoids. So every category is a groupoid. So he introduced a family of categories. In fact, claim is it's an operand in the category of groupoids. So it's a category, therefore we have operand structure on objects. And on object, this is what is called magma. It's an operand in the category of sets. If you like, this is parathene-sized permutations. And morphisms are just braids. So essentially, say for example, PAB3. What is it? Okay, I mean, it's a category, therefore say I take 1, 2, 3, and I put brackets in this way, then I take its permutation, say 3, 1, 2, take these brackets, and then the rule is I draw we draw a braid which simply connects the same labels. Now it makes action of permutation group perfect. So there is it's now a sigma operator in this category. Then Bar-Natan, then he introduces simply operat S, which is just the same. It's also operat in the groupoid. Essentially, you have unique morphism between any two objects. You forget braiding, morphisms become unique. So once you fix this condition, you have a map of operats which forgets braidings. You have kernel. Kernel is an operat. You can take I-adic completion. So essentially, you play the standard Maltsev trick when you choose some field. You want to have powers of elements to some real number. So you produce from this picture what you produce. He produced this operat PAB K. Oh, I forgot. Sorry. And now claim is that he defined automorphism group of PAB. This is precisely GT. But Drew is right. Really, to make this observation, one does not need the full operat structure. One needs just his operations because they still generate already everything. But yes, exactly.
This is
it's
not
all
useful.
yeah, we take. No, we take. No, okay, I need details. It's just look at the Drew paper how he completes it. It's an arc of Maltsev completion. So this is in fact Tamarkin. I saw it in the Tamarkin papers, and when I saw it, of course, every operatic, when he saw this, had a huge smile. But he used it. This is one of the ways to get to good object, to Grothendieck-Teichmueller group. What Tamarkin? Let me quote Tamarkin. Yeah.
Just a comment to the cube there. Drinfeld knew it all.
Yeah.
Obviously.
Yeah.
He actually uses it in a very clever way. To even pin down some action of the Grothendieck-Teichmueller group.
Yeah, maybe we'll
So.
Yeah. Yes.
Yeah.
But let me say something new, which in fact, I don't know, maybe. Anyway, I saw it in Tamarkin paper. So let us still look at this original operat before completion. So it's an operat in the category of groupoids. So we have a functor from, operats are good Pi. Any monoidal functor gives us another operat. Well, we have a good functor on category of small categories, Nurov, right? It now functor to the category of simplicial objects. So let us take new functor. So again, we get immediately an operat. So these are kind of chains of composable maps, like this, right? Let us take linearization over some field, the same field. It's a chain complex. It's a chain complex. It's in fact an operat in the category of chain complexes. And one of the starting point of Tamarkin that this is quasi-isomorphic to the chains of little disk, which Bruno described. So the fact that these are operats is kind of a... So this essentially, we come to the world of G-infinity algebras. It's not true to say that Gerstenhaber algebras are just polyvector fields. No, there is another important family, Lie algebras. There is a nice functor from Lie algebras to the world of differential Gerstenhaber in the back. So we come here. So this is his starting point. His second starting point, which I will need later to prove my claim, that above, is this operat. So we have an operat. So this is kind of one important point in the Tamarkin story. In the second point, he took the following functor. We have a functor from, we know that any Lie algebra is what? It's a codifferential, right? In some coalgebra. So that's a Chevalier-Ellenberg functor. So we map it to co-commutative codifferential coalgebras. Coalgebra, category of coalgebras. So we take T, we take symmetric product T shifted. That's Lie bracket gets encoded into differential, and this is operat in the category of complexes. The second observation of Tamarkin, which he used to prove the formality theorem, is that cohomology of this operand is precisely G, the operand of Gerstenhaber. So in fact, this is how he could his formality theorem of the formality of little disks. He starts here, comes to this chain operand. This is easy. This is easy. Then he uses choice of associator to come here, and then he completes this story. Okay, I will use this fact later, that homology, no, in fact, I would say even more, they are quasi-isomorphic. Now we can say they are. So this operand and the operand of Gerstenhaber algebra are quasi-isomorphic. It's formula. Right. So, operatic understanding of what Drur has written is useful. It's one of the, which really, I mean, Tamarkin made it absolutely impressive. How he uses his interpretation of original Drinfeld results. My second comment is you ask a good questions about zeta values in deformation quantization theory. It's a good question. I mean, we had talks on multi-zeta. What is known about it? Let me just give some details. Question was about zeta and multi-zeta values in the Kontsevich formality story.
Yes.
Let me answer in detail. I said something, but I mean, I want to be precise. So, what we know, I mean, Kontsevich gave, in fact, us two formality maps, one with full proof, another with no proof but with the correct claim. So, remember, his formality map.
Correct claim.
Yeah.
Correct claim, false proof. False proof.
No, the proof was
Correct,
obtained.
false claim.
The proof was obtained just very recently, and it is not even in archive, but it's done because it's the proof is beautiful, but it's far from obvious. So his formality map is essentially what? It's a sum of graphs which interpret as operators and some weights. So the weights are essentially, I mean, integrals of differential forms associated to the graph over some configuration space. So what are the weights? The weight, essentially, graph determines everything. All we need to determine weight is to define differential form. And he uses just propagators. So he produced two propagators. One is up to coefficient d argument. So this is the volume form of hyperbolic circle. And then another propagator he produced is this one, d log. So what we know about, I mean, the weight, to compute weight is a very hard job. So for example, I advise one of the kind of a nicest paper on computations is the paper by Michel van der Bery. Then, right? Yeah, so he proved that, now look at these graphs. You know, any graph gives you a form and therefore a number. So look, a graph which has the structure of a wheel, but with even number of vertices only.
Just step aside.
Yes. So n plus 1 vertices if I count the center one, and even number on the wheel. So he proved, it's a good exercise in the theory of analytic continuations of meromorphic functions. It's not a direct computation. He proved that this kind of, there are 2n, in fact, kind of a 2k vertices on the circle. So this is bk up to some factor. Bernoulli numbers all occur. So rational numbers. So the problem is, I mean, can we find at least a candidate for irrational or even transcendental? And this was done by Wilwache and Felder. In 2008. They considered, you know, the graphs can have vertices on the line and the others in the upper half plane. So they produced remarkably complicated graphs. 3, 7, yes. So 4 go here. 3 come, observe. 3 come here. they're all connected in this way. And I think there is this one. So the proof is highly non-trivial. It's also an ingenious calculation. This is modular rationals. This is zeta 3 squared pi squared mod q. And this is all we know about this propagator. What about his second propagator? It's my result. In 2008, I studied now these wheels for any n. For any n. And I proved they are zeta n to pi up to the n. And I can tell you, my proof does not work for that propagator, and his proof does not work here. So it's a very two different stories. So for this propagator, they're all there. Right, now why I also mentioned these two propagators? Because according to Tamarkin, again, one of the corollaries of Thomas' result is the following. There was a question. Kontsevich produced us one particular formality map. Tamarkin proved there is a kind of a family of formality maps on which one for each associator. But maybe there are others. No, the answer is, this is Tamarkin's construction gives now the full set. So essentially, GRT acts up to on all formality maps up to homotopy, gives full classification. Therefore, for these two formality maps, there are some associators must be there. So conjecture was that this one, this singular, no, it's a singular one. When the 2 points collapse, it's divergent. This is why the fact that the weights converge is not obvious at all. Yeah, it's not obvious at all. This is the job. In fact, this propagator does not extend to compactification. It's singular. Still, the weights conversion is proven why. We understand it. So, in fact, this is Knижник-Zamolodchikov associator, and this is a new one. This comes from a new Alexei Tarasyan. This was another comment of mine. Let me give now a few just words about this new associator, about it. I believe it is very important. In fact, for some problems which, for instance, Brown outlined in his talk. Yeah.
A reasonably naive question. Is there a connection between the Kontsevich formality theorem and the formality of braid groups, of pure braid groups? Because the formality of pure braid groups is given precisely by the Kono-Drinfeld theorem, and then GRT acts on and precisely any associator will give you a Kono-Drinfeld.
Yeah, but I don't see any connection immediately.
Because you've been mentioning
conjecture. It's sort of saying the little discs operand, C2.
I know, but
you'd have to check the formality, make formality of operands.
No, but formality relates to concretely algebras. Very concrete.
Yeah,
but part of Tamarkin is to say that the algebra, the Gerstenhaber algebra operand is formal. And I think that's part of this proof.
Because in Drinfeld paper is a proof of formality after Kono.
Yes, and so this is inside the...
And the isomorphisms are parameterized by
So
associator.
what you said, it's inside the proof of Tamarkin of
Yeah.
the formality of the little disk operand, which he uses to prove the deformation container.
Yeah.
So it is.
It is, yeah.
No, it's slightly. He used Itigov-Kardan quantization theorem to prove formality.
It's several things.
Yeah, he used, but one of the central things is that theorem. It was crucial. Itigov-Kardan proved that there is a universal quantization free by algebras depending on the associators. And this is how he got it.
He uses it, but that's harder than the thing we're just talking about.
Yeah.
That's a bigger input into
Okay.
than the thing we're just talking about.
I didn't get the question. Anyway, let me continue on. Let me say a few words about this new associator and why it is really great. So, common 3. No.
What is exactly the definition of the differential form? Z1 minus Z2 over...
Yeah, imagine I draw this graph on the plane. Imagine I draw the plane on the graph on the plane. I have some points assign.
No, but I want to look at the formula. What is the formula for omega 1?
What is the propagation?
I explain. I draw this graph. I draw this graph on the upper half plane.
But before you explain, what did you write?
The question is, I put points. I draw my graph.
Z1 minus Z2 over
Vertices become points in the plane.
Just in the formula, they have to which are functions.
there is a bar missing. There's a bar missing.
From a distance, it's difficult to read.
What is missing?
They want to see Z1 minus Z2, Z1 bar minus Z2 bar. I think they want to see a bar there. They would feel much more comfortable.
Here?
Yeah.
There is no bound on that too.
The trouble is, d-arg looks like d-log.
Yes, that was my problem.
It's a volume form on a hyperbolic circle. It's not. This is correct.
No, but I could not distinguish the writing of
Sorry.
d-arg and
No.
d-log.
This is
That
correct.
was my question.
But now, I mean, what you want to see, you will see now in a second in the formula for Antonov Tarasyan, because I will have this another conjugate. So.
That's not
Right, so Knižnik Zamolodchikov comes from a very simple, I mean, essentially, we have a family of flat connections, right? We have a family of flat connections on the modular space, on the configuration space of n different points and different points in the complex plane modular. So we can dilate, complex translate. So, I mean, this flat connection lives, there is a family of flat connections. And they're defined just as the sum for I less than j, generators of the Conrad-Drinfeld algebra in the nth part, and d log of zi minus zj. So this is okay, yeah, I mean, so. Drinfeld associated is produced as a regularized monodromy of this connection for n3. It's an interval. So n3 is an interval, of course. The new connection is also for, this is kind of Knižnik, or maybe it's Drinfeld, in fact. Well, connection is Knižnik-Zamolodchikov, right? There is a new connection produced by Alexeyev and Tarasyan. Again, it lives in the same space, but this time it looks like Kontsevich formality maps. I mean, it's a sum over some graphs with some weights. So now graph have two types of vertices, one kind of white vertices and black vertices. And how you produce the weights, you essentially consider these black vertices which lie as dummy, you consider push forward. And kind of, okay, let me give a picture, say this one. So assume white are 3 points in complex plane which are fixed, they are not moved. Black is moving, and I consider this graph. It's a 3 form, right? When black vertices is allowed to move, I get a 1 form. Therefore, so these weights in fact are 1 forms. Now, not numbers. I put C gamma, okay, but it's kind of a C large. They're now 1 forms. So it's a sum of such graphs. Say, for example, this will contribute. And then there is a rule which reads, when you can read from such a graph an element in Tn. Now, for example, this will lie in T3, and this will be commutative of T1, 2, T2, 3, and so on. So this is highly non-evident flat connection. It is flat indeed. In fact, I mean, these forms are single in general. But the point is, you can compute monodromy without any regularization, provided your path is semi-algebraic, given by inequalities or in polynomial equalities, because it's what is called by Kontsevich PA forms. So this is a very amazing, and therefore, I mean, monodromy, genuine monodromy, gives us a new associator. But what is the point? On this graph, we can write explicitly action of GRT. So if we kind of can prove that, I mean, these are multi-zetas essentially, the weights. It is related to, possibly related to what you said about action of motivic on motivic zeta values. Because this is, again, I mean, we speak about not the action on rectal values, we use action on graphs, but graph gives us a pair, configuration space and the form. And again, formula will be explicit. So this is why I think it's a great associator.
What you're saying is if you use that,
Oui.
if you use that one for the formality map,
Yes,
you will get multi-zeta values. Is that what you're saying?
No. I mean, we don't know what are the coefficients. The question is, what are the coefficients of the new associator?
Yeah.
So it's again a formal power series. Antonov-Tarasyan associator is again a sum of power series and non-commutative letters. But what are the associators? I mean, we have to compute now weights of this single algebraic form over integrated integrals of this one. What is it? It's this. I mean, it's beyond.
You don't know.
I don't know. But conjecture is it is still that space. Right. So this is third and now I can prove my claim and explain a relation of the deformation of a line with Furusha's theorem. So now I start item 2 in my story, GRT and deformation theory of maps of operas. Okay, one of the again, deformation theory of operas was well developed. But I don't think anyone ever thought, let us compute what are cohomology groups, what are infinitesimal tangent space, I mean everything. This is what, in fact, Tamarkin did first. He started deformation theory of the following. I mean, we know operator of Gerstenhaber algebras, two operations, Lie bracket and commutative. Therefore, there is a map from operator of commutative algebras to operator of Gerstenhaber algebras. You can construct deformation complex, the Gili algebra out of it. So this is what? I mean, you essentially replace com by com infinity. And then essentially the vector space, this is the set of all equivariant maps from generators of com infinity, degree shifted by 1 to G. Still, it's not doable on this one. It's not possible to make any computations, but what Tamarkin did, remember, I introduced you an operand T1, Chevalier-Eilenberg construction of T with its differential. And I said, I mean, he proved it is quasi-isomorphic to G. Therefore, I can replace. And no, when I consider deformation theory, I have a freedom up to quasi-isomorphism to make a replacement. So he replaced it by that operand in the category of coalgebras, differentials. And now and then he proved that H1 of this complex is GRT. But of course he proved it in a very funny way. These are two last sentences in his paper. My claim follows that this is true. Full stop. The paper ends at this moment. So why is it true? In fact, the proof is not that hard. That's surprisingly. So he stopped it, but he had a reason to stop. So why is it true? So, I mean, now it's easy. We know what are the generators we went, right? These are kind of a Carolus associated degree 2 minus n. But it's important now, I mean, to see what is going on. I mean, the Carolus are not they satisfy shuffle conditions. There are algebraic conditions on Carolus. They're not arbitrary. And it's easy to compute what are degree 1 element in there. And for some reason, it's enough to consider the situation when we take just T1. So what are the maps from such a corolla to T3 now? It will be N3 because it's En Tn. For degree 1, N must be 3. So I mean, any such a map is given just by this is some element formal power series in the completed Lie algebra of T3. But then it must be cycle, right? In fact, one can check. I mean, nothing comes from coboundaries. Coboundary set is empty. All you need to check is cycle conditions, so it's easy. You have to check that delta, let me denote this by phi. Delta of this phi is 0. By the way, what is this arrow? Remember, this is a map which sends multiplication to multiplication here. In this picture, it sends multiplication in com, in fact, to 0 in T2, into unit in T2. Yeah, so this is the map. This is my map rho, which I default. So what will be the equation for this phi? It must be 0. What it means? Well, in fact, what I need to compute, I now to consider, now the value are determined on triple Carolus. I have to consider differential on the 4-tuple corolla. And you know, this is a phi term. Up to sign, this is what? Oops. Five terms. What it means to be a cycle, it means binary vertex is decorated by image of row, in fact by 0. And now we take a periodic composition in this opera T, and I told you it's non-trivial composition, even 0. This is my phi. This is this some Lie word in T3. This is phi. This is again. So I take. So this is pentagon equation. It's exactly pentagon equation. So it's just such an elementary exercise. So this is a pentagon equation from definition of GRT. Where hexagon come? Okay, they come from the fact that this is not S infinity. This is com infinity. It means there are shuffle relations. There are two basic shuffle relations. So it's 2, 1, 3 plus 2, 3, 1 is 0 on the generator, and one more. So therefore, this phi must satisfy this relation. These are two hexagon equations. Exactly. So we recover GRT in the classical form with hexagon equations present. But now this gives kind of us a question. I mean, what is the difference between S infinity and com infinity? Precisely these two relations. So what the question is, I mean, this is a problem Thomas did. This is how he proved Furush's theorem. So kind of, let me first assume Furush's theorem is true. It is true, but let me just, for my argument, sorry. I just want an implication. So for this moment, let me assume Furush's theorem. And this theorem tells us, okay, all I need to check is this equation. I can forget about shuffle relations. I can forget what happens so far. But this means essentially that I essentially study the first cohomology group of the formation complex of S infinity or S into Gerstenhaber. And essentially, I mean, if I, again, assume your theorem, I immediately conclude there are GRT sitting, because this is already decides everything. I don't have shuffle relations already there, but there will be some extra element. Clear which one? It's a commutator XY. It solves pentagon, right? So we have to add. Once we delete hexagon, this solves pentagon. This is the theorem of Milwaukee. So essentially, your theorem would imply this, but he gave independent proof of this. So this implies that it goes in both ways. In both ways. So once we know this, then kind of we immediately see. I mean, this play no role at all. Shuffle conditions play no role. We can ignore them. So well done. So kind of it means essentially for apparatchiks, Furush's theorem tells that deformation theory from com and from us are almost the same. Kind of deformation theory does not distinguish. Therefore, hexagon equations are not necessary.
Excuse me, so in my proof, I give some condition, kind of normalization condition in the quadratic terms.
Yeah.
Quadratic term should be 0. The condition was necessary.
Yeah, I mean, so I mean, yes.
Oh, this part.
Yes, this is what I mean. There is extra term. You simply say it's not present. You eliminate it. We just add it because it's a theorem. It must be there. This is exactly your extra condition comes in. Because we study all possible deformations, and I told you that in fact, again, that's a commutator. It solves pentagon, but this is not a GRT element. Therefore, it comes out, of course. Right. And now I'm in this story about the line. So, okay, I take a plane, I draw a line, and I want to study its deformation theory. It's a fine geometry. You can say, okay, what I can do? I can move it, I can dilate, can rotate. So kind of, there is a group X which preserves my embedding, a fine embedding. Now this, in this group, I mean the group plus, okay, there is some, I don't know in which direction I should write it. It's contractible, right? So let me say that, I mean, deformations which are related by this guy are trivial. So essentially, I ignore them. Rotations for me is not. It gives some cohomology class. It's this one. Let me keep it. So I want to deform it. Now, of course, kind of it looks like, I mean, what I can do, nothing. But let us change the point of view. For physicists, a line is not a line. For what physicists do? They throw points. Whatever they compute, they work with configuration spaces on manifold. This is where all the results of Feynman integrals come. Therefore, instead of a complex plane, so what I have started with, I have drawn a line in C. Somehow embedding, affine embedding. But now, kind of again, I take a physics point of view. I consider configuration space of n points, n different points in complex plane, no modulo this group. Let me say this, yes. Again, I don't remember, I mean, which. Right. The same as a line. I mean, a line for them is also kind of a, I mean, some points can lie outside, some inside. Therefore, once I have drawn a line, I have a map for any n. No, in my case, I have to take n greater than 2, right? To make, yeah, I mean, because otherwise still a point. I mean, Cn of the line, and kind of, I mean, it will be grouped now. Translations and dilations. And I have, for any n, I have an embedding, and this is equivalent. I can assume my points are numbered. So this is equivalent inclusion of, in fact, a nice smooth manifold. They're non-compact. So it's a family. But again, for physicists, this is what? This is an area, this is a domain of integration. And it's very bad it is non-compact. This is always their problem. They define something, integration of this space, but it's not compact, and therefore it diverges. So for mathematicians, what we should do? We should compactify. We should compactify. And there is a natural Fulton-McPherson, it's a real Fulton-McPherson compactification of this inclusion. So once I have drawn a line in the C, I have this map. And then when I compactify, standard Fulton-McPherson collapsing points, I have a map. So, okay, so let me denote this kind of a CNR, and this is CNC. So, I mean, this inclusion extends to compactifications. It's easy to see. So, in fact, I have now a family of maps from CN compactified to C compactified. But once I made the compactification, we've got some extra structure on these spaces. They're both operods. They're both operods. In fact, they're free operods in the category of sets. If you forget topology, they're simply free. And once I draw my line, in fact, I have now a map of operods. And remember, I mean, okay, I cannot define what is a deformation theory of map of topological spaces. I know how to do deformation theory in the category of vector spaces. Well, it's clear what we should do. We should take chains, a function to the vector spaces. So we take chains of my drawings of this space.
By the way, what is pi 1 of this graph?
Sorry?
You take a fundamental group as well.
Which of?
The discussion we had earlier.
Which of?
Compactification of the plane. Don't you get again this braids and
Yes,
together
yes.
with
You should take group
associativity?
point. You should take group point. Yeah, I mean, yeah. So right.
This compactification
Yeah,
is
you should.
manifold with
Yeah,
coordinates.
sure. Group point
It
of
doesn't
this.
change the fundamental group.
No, because it's manifold with coordinates,
Right.
so topologically it's a manifold
So
with
you
boundaries.
get PAB back.
No, moreover. In fact, fundamental group point of this compactification, it contains this operad PAB as a subset. Why? I mean, you can consider precisely points which like the line. Yeah, this is so. It is here. This is so. It's related to the story. In fact, Amarkin used it in his proof that when I take the nerve, oh sorry, I should take nerve of PIB, not PIB, I apologize. It's a nerve, it's stupid what I said. If you take now chains, the chains here, it's a quasi-sum of phi.
Yeah, you mean C,
Yeah,
C bar on that,
yeah.
not minus
Yes,
C
yes. So, but now I have a map to chains in the complex plane. Okay, for this I have a well-defined theory. This is what? This is G. This is what? This is S. And I know deformation theory.
So what's the symbol you said again?
This is operator of associative algebras.
Yeah.
This is operator of Grothendieck-Teichmueller algebras, homology
This one,
level.
this one is
And
the
yeah,
associative
yeah.
group. This one is the
Yes,
associative
yes, yeah. So essentially what I study deformation theory of S in G.
Yeah.
So this is what a line in the plane is. This is the point. Nothing but kind of pleasant. Pleasant to see. So indeed, when we go to chains of my drawing, we recover GRT. So I have 15 minutes left. So I have some time to answer my third questions. Why GT is deep? Because our two previous answers. Drew said, it's deep because it relates to different universes. You said it's deep because there is motivic velocities. For me, it's deep because it's geometry. It acts on polyvector fields in a very interesting way. In a very unusual. Now we go to basics of classical geometry. So now I use what John explained in his lecture notes. Formality maps of Kontsevich. So point one. Kontsevich gave us a formality map, which is the what? This is a Lie infinity quasi-isomorphism from the Hochschild complex of some smooth algebra of smooth functions on a fine space, to it's a differential graded Lie algebra, to the Lie algebra, say I is to the algebra of polyvector fields in Rn.
It doesn't go in the other direction.
Yes, of course, it's up to homotopy. This I will now use. It's a Lie infinity quasi also up to homotopy. It's I will use it now. Wait a minute. So and so this is Kontsevich. Tamarkin said that in fact there are plenty of such formality maps, and now that I told you, Wilwacher did it. They are classified by GRT. They are classified by associators precisely. So, but Tamarkin said, in fact, there is a family of such maps depending on the associator. Therefore, what we can think? Okay, now let us take one associator, we have one map. Let us take another associator, we have another map. But because they are Lie infinity quasi-isomorphism, I can invert up to homotopy. So there is, in fact, Lie infinity map from here to here associated to this associator. So I can start on polyvector fields as just with a Schouten bracket. I have a Lie infinity map here using one associator. Then I have a Lie infinity map back using another associator. So two associators produced me a Lie infinity automorphism. Two associators is a point in GT. Right? They're different. I mean, its action is free. Therefore, what I get, kind of an element of the group which relates these two associators, acts up to homotopy. It's not a real representation. It's because we the inversion is not canonical. But the question is, so G and GRT, we have some action. And the action is universal because Tamarkin constructions do not depend on any dimension. They're just true for any space. They're universal. The right way is to understand in terms of operands. Yeah, I mean.
Could you repeat the sentence? I just didn't hear it.
So formality map is a map of two operands.
The right way is?
The question is how to define universal formality map. What means universal? Applicable to any Rn. So the right way is to reformulate it in terms of operand. This is a map of some operands. And the choice of N is a choice of representation. This is what I think. All right. So, but the question is it a homotopy non-trivial what we get? That was not clear. But what follows from, again, Thomas-Lowacke theorem, that we do have, so this action is homotopy non-trivial. With another way, GRT acts just on one of the basic structures in geometry. What is a manifold? Essentially, we need manifolds to define smooth functions. Vector fields are derivations. So it acts on the algebra, wedge algebra of derivations in a universal way. So for me, this is very deep, and it is homotopy non-trivial in the universal map. Yeah, so this is a very deep fact. I mean, I think it will change the notion of a manifold somehow. I mean, we shall use it as a gluing sometimes, and sometime later it will be inside gluing map, something like this. It's a very deep sense. Acts on all Gerstenhaber algebra. You know, it's very simple. I mean, no deformation quantization, no Hodgkin complexes, just Rn polyvector fields, and you have such an action. That's amazing appearance of GRT. And it did appear. I mean, the point is, what means homotopy non-trivial, by the way? It means essentially the following, that if you have, you know, Maurer-Cartan elements are called Poisson structures. Maurer-Cartan elements are called Poisson structures. So these are is equal to 0. And essentially it means that given any Poisson structure, you can produce a new one for any element in here. You produce a new one, pi of g. And there is an explicit formula due to myself, which, well, yes, now they are not due to myself. It was then joined with Thomas-Lowacke and Carlo Rossi, sorry. So there are explicit formulae which gives us, it will be again a sum parameterized by graphs with some weights. Weights are computed in a new way, not like in the Kontsevich theory, not in a, like for AT associated, in a new way. Again, it will be singular differential forms, but thanks to the theory of Alexeyev, Tarasyan, and Rossi, it converges. And so it's a very explicit formula, it's highly nonlinear in pi, and all powers occurs, and for convergence, of course, we need some power, number of vertices of the graph for all parameters. And then another result due to Thomas and myself, Thomas did most of the job, I should honestly say, is the following one. All the complicated job are due to him. So there is another class of structures which are useful in quantization theory. They are called, this is called BV formalism. It's a name. But in geometry, this is what? Instead of usual manifolds, they study odd symplectic manifolds. Odd symplectic manifolds. On odd symplectic manifold, there is a canonically defined semi-volume form. And out of such a choice, you know, what is the beauty of Skelton equation? It is differential invariant, without any choice of connection. It's just, in a similar way, there is an analog of this equation which uses some second order operator and something which looks like Skelton bracket. But it's a different world, it's a different automorphism group, it's a supergeometry. So the claim is, in fact, for finite dimensional manifolds. So this is not a real quantum field theory. Our theorem is GRT acts here, but if for this statement it is just enough to use his kind of main theorem that zero cohomology graph of Kontsevich graph complex is GRT, for this to make this extension to act to BV, to master functions, one needs extra data. One needs vanishing of all negative cohomology groups. Oh, wait. So this is not obvious at all. So this is possible to extend. So the action is different. It uses all this. You always resolve abstractions in negative degree. They contribute terms which act on such master functions. So it's a very different action. Well, this is it essentially. So I'm fine.
Can still ask a question? feel free to ask. Do you have any question?
Yeah. You looked at the deformation complex between the commutative operads and the Gerstenhaber operads, but then said you could just look between the associative operad and the Gerstenhaber operads. But the associative operad and the little disks operad are sigma cofibrils. So can you calculate the deformation complex over the integers between the associative operad and the chains on the little disks operad? And is that very different from the rational case?
No, characteristic 0 is crucial. It's absolutely crucial. I mean, we often need homotopy transfer in this story. And I think if characteristic not 0, I cannot even invert Lie infinity morphism, so it doesn't work. Over that, I don't know the answer. For me, it's not evident at all. Even I don't think even the machinery can be applied to your question.
Can the deformation complex be applied? I know the rest of it.
Again, at the end of the day, I mean, when you start with these deformation complexes, he reduces a problem to a particular complex, I mean, which is relatively small. It's just for fixed and it's finite dimensional, with a clear differential. While you're talking now about infinite dimensional, it looks like completely different, very complicated problem.
I have a question. The deformation complex of the map between us and Poisson is related to Vassiliev invariant of knots. Poisson is not far from Gerstenhaber. There's just a degree. Do you see a relationship between these two things?
I mean, in fact, there is a family of these concentric graph complexes.
Yes.
There is a family. So essentially, what we were talking about, but still it's not Poisson. This family does not include Poisson. Essentially, there is a two-dimensional complex. It's responsible to Gerstenhaber. There is GC3. That's the bialgebras. And I mean, methods which Thomas used in GC2, again, I said him, he said they do not work on GC3, but I mean, I looked, so his result that GC2 is GRT, I don't know, I mean, maybe I made a mistake, but I claim this is just trivial. This is nothing there. But, okay. But I think it's easy, but still, I mean, it's not published. So this is a kind of a, this is what? This is a multiplication, Lie bracket in degree minus 1. This is multiplication, degree bracket minus 2. So Murray-Cartan elements are Lie bialgebras. Somehow, I mean, it's completely different. I mean, the reason why it is so simple, because there are simply not enough good graphs of degree 0. So it's not a big deal to see it. But of course, the question is about high cohomology groups. That's even mystery here. I mean, the question is it true that H1 of GC2 is 0 or not? Or 0? Why it is a good question. Okay, we have scout and bracket on polyvector fields. Are there other homotopy non-trivial? It's a mystery. Moreover, strange enough, Thomas' technique does not give an answer. But Thomas found using computer simulations, but then he said, in fact, Drew found GC2 is non-zero. Some computer simulation, I don't know, it's his play. So there are some high cohomology, but H1 is it's good to know, it's useful to know what happens with this counter.
Any more question? Okay,
So in a talk you said associator, Alexander-Torosian associator. This also satisfies pentagonal hexagon equation.
Yes.
So they are formal power series with two variables.
Yes. But the coefficients, I told you, we don't know. They are integrals of these semi-algebraic forms of simplices, essentially, again. But now they're singular. They are. I mean,
Sorry, this what you two. I mean, you wrote Rn everywhere, but can you do it on a manifold? Can you glue it?
yes. It's
So
no problem.
This is natural.
Yeah, I mean, kind of the main thing when you can glue, when your graph are at least trivalent, This is a kind of a general thing. I mean, it's from fields of resolutions of polyvector fields. Once you essentially all the stuff lives in trivalent and high graphs, it's globalizable. It's a kind of general principle. If it's low, it does not. But all this stuff, formality theorem, these actions, the infinity action, they use all the trivalent and high graph. It's no problem to extend.
So it's on any graph?
Yes.
So I have a question which might be more to Pierre Cartier, but the point is that Kontsevich got this formula by taking a kind of Feynman integral and then a flat integral and then doing Feynman expansion. And my question is that there was long ago the dream that the renormalization group would be related to Galois or Galois over Q or GRT, and so this could be the place where this could be checked because it's a kind of field integral and there's already GRT there. So my question is is it meaningful to try to do renormalization for the field theory which gives rise to this F?
Yes, look at this. I said it's a finite dimensional master function. It's crucial because all this, it's again the sum of the weights of the Feynman graphs. But the assumption that this S lives on finite dimensional is crucial for convergence. Once I use a genuine quantum field theory where this odd-symplectic manifold is a space of functions, it's a functional space, it's infinite dimensional. Regularization must be looked at. So to define action, what happens on a real quantum master function, say for example the one defined by Catania and Felder, there is a version. There is a beautiful solution. I cannot apply that. You need to regularize it. I have a formula for GRT, say tetrahedron graph, but it diverges. So you need to do something. Regularization is crucial to continue this story. On Poisson, you don't need it. Okay, provided it's a finite dimensional again. But for here, we need infinite dimensions. But it doesn't work. I mean, finite is crucial. The reason why crucial, you have to use graphs what is called with closed paths, with wheels. And I mean, in infinite dimension, they become traces and they explode. When you do representations, in terms of graph, it's no problem. When you try to represent, they explode. So you need regularization at the stage of representation.
Another question?
Okay.
So, thank you.